Welcome to our tutorial on op-amp basics part 2. Okay, so in this tutorial what we're going to basically do is that we're just going to continue from where we left in part 1, and over here I'm going to introduce you to the several interesting properties of the op-amps. Okay, so there you go. Now these properties, okay, are quite critical to your understanding of the op-amp functioning. Okay, so there we go. Just put it down somewhat like this. And now before I move on to the properties, okay, I'll just like to draw or rather reference the the equivalent circuit of the op-amp that you had come across previously in part 1. So there you go. So this is pretty much the diagram that you had come across there. Okay, just kindly bear with me for some time. Okay, so there goes the dependent voltage source with ground. Okay, and there we have the output resistance and the output terminal. So that's pretty much done over here, and its magnitude is given by A times VID. Okay, just hold on for a second, please. Okay, so there we go. So that's done. So basically this is the equivalent circuit diagram of the op-amp that you had come across previously in the part 1 of this tutorial. So here I'm just going to point out some properties, okay, that you would like to know and improve your understanding on this subject. So over here we have the resistance at the input. Okay, that's the input resistance, and here we have our output resistance, characterized with symbols Ri and Ro respectively. So here, if we just recapitulate once again the properties we had already come across in part 1. So that's property number 1, is that the op-amp has a very high gain. Okay, so the op-amp has a very high, or rather I'll just not call it gain, I'll just call it open loop gain. Okay, so there we go. The op-amp has a very high open loop gain, characterized with the symbol AOL, and is approximately 10 to the power 5 times that of the input difference signal, that's VID. Okay, so now again we had come across another property of the op-amp, that it's got a very high input resistance. Okay, so there we go. So there's a very high input resistance of the op-amp, characterized by the symbol Ri. And now we can see here that the input resistance of the op-amp over here is indicated right with this yellow circle at the in between the two input terminals from this equivalent circuit diagram. Okay, and now we had also known that the op-amp basically has a very low output resistance. Okay, so it's got a very low output resistance, and it's basically designed to have a very low output resistance so that it could output a lot of current to drive many devices as such. So here, if we're just gonna give you some values as an idea, then we're just gonna refer to the op-amp chip, that's MUA741 IC. Okay, so this op-amp is available in an IC package, okay, and is one of the most general purpose basic op-amps. Okay, and it's still in use today, although it's become obsolete in the industry, but it's still in use today in order to train beginners in electronics courses on op-amps. Okay, so just to refer to this IC for the respective values. Okay, so the input resistance of the MUA741 IC is approximately something of the order of about 2 mega ohms, and the very low output resistance of this MUA741 IC is not actually known by me. I actually don't remember its exact value, but it's of the order of a few ohms. Okay, it lies in the ohms range, and it's of the order of few ohms, not much. Okay, so I think that's not going to be a very big of a problem. Okay, so now we're just gonna come across the other interesting properties which we haven't dealt with in part 1. Okay, so here I'm gonna introduce you to the other new property over here, that the op-amp should have a very high common mode rejection ratio. So there you go. So that's common mode rejection ratio. Okay, so here, so common mode rejection ratio, that's quite a mouthful. So we can call it CMRR in short. Okay, so the common mode rejection ratio here actually means that how good the op amp is, at neglecting the common mode signals, okay, and amplifying the differential mode signals. Okay, I know that's quite a bit of terms there, so I'll just like to simplify this topic. Okay, so imagine that we have applied two input voltages, basically V1 and V2 at the non-inverting and inverting inputs of the op amp respectively. Okay, so now it could happen that there are certain common voltage components present in V1 as well as V2. Okay, quite the same components present in both of them, like noise and several other components that are possible to present in both. So for the common components present both in V1 and V2, the op amp is very, very bad at amplifying these common components present in both the input voltages applied to its both input terminals. Okay, so we can say that the op amp offers a very low common mode gain. Okay, so here I'll just use the symbol AC to just denote common mode gain. So the op amp is offers a very low common mode gain. So that's the characteristic of an ideal op amp in this case. So other than that, if there are certain voltage components in V1 that are absent in V2, okay, the op amp amplifies that quite, or rather pretty well. And similarly, the voltage components that are present in V2 and absent in V1, the op amp also does amplify those components pretty well. So what we see here is that the op amp is pretty bad at amplifying common mode or rather voltage components that are, input components that are common to both the input voltages applied to its both inputs. Okay, and it's quite good at amplifying the input component, the voltage components that are present, that are present in one of the inputs and not in the other one, in a pretty good manner. So basically what the op amp does is, for the case that it amplifies pretty well, okay, so it amplifies the voltage components that are present in one of the inputs, okay, and not in the other, okay, and vice versa. So basically the op amp, I'll just like to call it as differential mode gain. Okay, so this term that the actually represents the differential input voltages that the op amp is actually quite good at amplifying. Okay, so I'll just call AD as the AD would denote the differential mode gain. Okay, so there we go, differential mode gain. Okay, so differential mode gain actually represents that gain, the gain provided by the op amp in terms of amplifying the voltage components present in one of the input voltages and absent in the other. Okay, so the different or rather the difference of the input voltages respectively, that is. So ideally the differential mode gain of an ideal op amp must be very high. So the CMRR, that's the common mode rejection ratio, could be mathematically expressed as a ratio of the differential mode gain and the common mode gain. Okay, and it needs to be as high as possible. Okay, now this has an advantage that if there is a noise signals, there is so any bit of noise in both the inputs, at both the input voltages applied to the op amp's input terminals, so then due to the common mode gain being very low, it could just be attenuated. Okay, so that's one of the advantages of this system. Okay, so let me just come to the other property over here. That's property number 5, that will just introduce you to the term known as slew rate. Okay, so there we go. Now the slew rate is actually the property of the op amp. If I just denote it by S, okay, it could be mathematically represented by the variation of the output voltage with respect to time. Okay, so we just mathematically express it as dVo dt in calculus terms. So the slew rate basically expresses, or rather it actually implies the rate of change of the output voltage, okay, Vo, with respect to time. Okay, so this needs to be as high as possible. So y'all might be wondering as to why do we need this. Okay, so I'm coming to it in a moment. So they said that the slew rate needs to be as high as possible, and this the requirement is such because if we just subject the op amp to high frequency input voltage signals. Okay, let's say yeah, we have a high frequency input. Okay, so that's a high frequency input to the op amp. Okay, so if we have a high frequency signal at the op amp's input, then we would expect that the op amp to amplify each of these components properly. Okay, so we would expect an amplified version of this high frequency input signal right over here at the output terminal of the op amp. So now if the op amp's output voltage doesn't vary at the same rate of variation of this input signal, then this result would not be obtainable. Okay, so just keeping this in mind, it should should imply, or rather it does imply, that the output voltage in order to maintain the same phase as that of the input voltage signal right over here, even at high frequencies, it's necessary that the op amp has a high slew rate. Otherwise we won't have this sort of stable operation. Okay, so it needs to be as high as possible, and it's basically becomes important at high frequency operation of the op amp. Okay, so there we go, high frequency operation of the op amp. Okay, so having discussed about slew rate, I'll just quickly move on to the sixth and the last most important property of the op amp. That is, an ideal op amp needs to have or rather has an infinite bandwidth. Okay, so as you can see here, for all the voltage amplifiers previously that you've already come across somewhere in the textbooks and in your courses and all, so for all the voltage amplifiers, they would have a curve, okay, a gain versus frequency curve that would look somewhat like this. Okay, so if we just take this point over here as the point, as where the gain is root 2 times of the original value. Okay, so there's the peak gain. So at these points, okay, which is referred to as just occurring at the points f1 and f2. Okay, so at these points, okay, basically what happens is that the gain of the op amp remains fixed within this region. Okay, so in between these two frequencies, that is f1 and f2, the gain of the op amp remains fixed, which is basically termed as not of the op amp actually, sorry for my mistake there. So the gain of an amplifier basically remains fixed in between these two frequencies. Okay, so the f1 is termed as the lower frequency and f2 is termed as the upper frequency. So now the bandwidth of this amplifier under discussion would be given by the difference between the two frequencies. So the range of frequencies occurring between them is actually the bandwidth of the amplifier under discussion. But an op amp has been ideally thought of such a device which could provide equal gain, okay, which could provide equal gain for all possible types of frequencies that could exist basically. So if we have the if we just try and draw the gain versus frequency curve of an ideal op amp, then it should look somewhat like this. Okay, it should be a straight line with constant gain for all the frequencies and till infinity. Okay, so this was the case for an ideal op amp. Okay, so I just mentioned it over here. This was the case for an ideal op amp, but as I said, that practical properties deviate a bit from the ideal desired characteristics. So the actual, or rather the practical op amps bandwidth, or rather this gain versus frequency curve, would look somewhat like this. Okay, it would have a large bandwidth there. So if we just take this as a by root 2, okay, so it would have comparatively a larger bandwidth over here. So if this is f1, that's a low frequency, and f2 over here, so we can see here that this bandwidth, okay, I'll just call it bandwidth 2 and this one is bandwidth 1. So over here we can see that the bandwidth 2 is basically greater than bandwidth 1 right over here. So an op-amp basically has a greater, or rather a quite high bandwidth, okay, as much as possible. So for the MuA741C op-amp, okay, the bandwidth is as high as about 1.4, okay, megahertz, okay. So for other op-amps, much improvised ones, have arrived today and is being created each day at various semiconductor companies. So for the newer op-amps, okay, now this bandwidth is even more higher. It's as high as about 4 megahertz. Okay, so having said that, we just come to the end of this tutorial, summarizing all the properties of the op-amps as much as possible. So hope you enjoyed that, and don't forget to watch the next tutorial on op-amps. But just till then, it's goodbye for now, and